engineers supporting customers in the areas of signal and power integrity, as well as EMI, EMC applications. Prior to joining ANSYS, David was a hardware design engineer where he led the design of high-speed Ethernet connectors. He also spent time as an assistant professor teaching electromagnetics courses.
Thank you everyone for coming today. As you can see, the title is sort of a mouthful. So what we wanted to talk to you guys about today is, there we go. So this is really an overview of what we're going to talk about. No big surprises here, sort of the motivation, the formulation of the problem, and then of course the results. And I'm not sure why that is still there. Okay, this is me, presenter. These are the guys that did the real heavy lifting. We have Secure from Microchip, along with some of my colleagues from ANSYS, not part of Synopsys, obviously. They were not able to attend today, so I'm here in their place, and hopefully I do a good job of explaining what they're showing. I see they've left time limits on these slides, so this will be interesting. So the idea behind this problem is that as we go into the AI space, we want to be able to have higher and higher bandwidth. We need to switch faster and faster, which means that we're going to need to have stable power delivery networks throughout our system. So what this work focused on was coming up with an efficient way, an accurate way of modeling the power delivery network for the PCI switch you see here. Okay. So, again, the idea is if we can accurately model everything in an efficient way, we can do a better design. What we've previously done in the past is done a split and stitch method. In other words, we have characterized each particular device, the IC, package, and a circuit board individually, created S-parameter models for them, which stitch them together. What we're going to show today is a new method that improves upon this process. So, as I said, the old method involves calculating each individual object or each individual component by itself, stitching the results together, and we were doing this for a single power rail at a time. To be more accurate, what we are going to do is we're going to use the ANSYS tool suite to compute all of the power rails at the same time and get accurate answers in a more efficient manner. So what we're going to do is we're going to use the Redhawk HC, or Redhawk SC tool to create a chip power model for the die. Then we're going to use, this is really careful, oops. Seem to be missing a slide. There's what I was looking for. This is what I wanted to come back to is we're going to use Redhawk to create the chip power model. We're going to then use ANSYS SI Wave. Inside that SI Wave tool, we have a tool called CPA, which allows us to add that CPM module that we developed with Redhawk for the die. Those characteristics then become part of the model of the package, which then sits on top of the printed circuit board, allowing us to extract the entire network all at once. So again, we'll go back here to the scene before. So what's the problem space look like? We have this 55 by 55 millimeter package. We have 4 power rails that we're interested in characterizing. And we're going to, as I said, we're going to use Red Hawk to characterize the die, and then the CPA tool to characterize the full system. So the first thing we looked at was characterizing the die. And this is one of the 2 big takeaways, I think, of this work that the authors really wanted to highlight was when we originally did this, we looked at these models and tried to simplify them as much as we could. However, in this case, when they did that, they found that when they looked at the transient noise on those power rails, it was quite large, as you can see in the red. What they found that they had to do was they weren't modeling enough of the die. So they had to include all the layers on the die, which then included the decoupling capacitance within the die. Once they did that, they found that the resultant noise on the power rail was very much reduced. So we take that new model and we're going to then attach that as a component into, as part of the package model. So the package, the die sits on the package sits on the printed circuit board, as you can see in the lower right-hand corner. We have those 3 components. We're going to model them all together. Why is CPA so good? It's a fast 3D EM solver that allows us to stack all 3 of these components together and accurately model them in a reasonable amount of time. So, once we've done this, we can now do a PDN analysis. We can go back and we can look at the impedance, the Z11, looking into that power delivery network, and we can determine whether or not we're meeting our impedance specs that we need to meet to achieve the noise levels that we need. Now, the authors were not working, or were not going into how do we optimize this printed circuit board and optimize this PDN. It's more wanting to show the flow that we were able to combine all 3 of these components together to come up with an impedance profile that was acceptable. Now, part of this, as you can see in the photo on the, I guess, upper right, is, there we go. In order to do this transient analysis, we need to take this to a transient circuit solver. So that solver is the ANSYS Nexum solver. And since this device has multiple power rails with multiple ports on it, as you can imagine, it can be quite tedious to set up this circuit model by hand. So as the last step of this methodology, we're using PyANSYS to automate the process of setting up the model and running the model, and then also setting up that circuit simulation. So PyANSYS is a Python-based automation language. It's an open source, so it's available to anyone. You can easily write code snippets to automate your simulation process. So this was really the final step that really brought this thing together and made it a production tool. So some of the results that they found after they had done this analysis, we had 4 power rails. All the results were within the area or the results were within the range of what they expected, so no surprises. The big takeaway here also is that the traditional method, or the old method, took 72 hours to solve a single power rail. Now we're solving 4 power rails. Yes, it took 112 hours, but this, when you think about it, they solved it all at once. So it's a great speed improvement. Yes, I know 112 hours is a long time, but the complexity, large complexity of the problem, it made it, this was an acceptable amount of simulation time for them. So it greatly simplified their process and sped it up as well. So finally, in conclusion, these are some of the things I've already talked about. By using this new unified method, they were able to accurately model their full power delivery network using the full suite of ANSYS tools, combining the die, the package, and the printed circuit board all at once. They were able to automate the setup to quickly get the results. And then the final takeaway also was to learn that they really had to be sure that they accurately modeled the die itself to include all the onboard capacitance to not give them erroneous results. So thank you very much for listening.
Thank you very much. Are there any questions for David?
I didn't understand the part where you talked about you had to improve the die modeling, you had to go to a lower level up to M8. Because I thought you mentioned something about the min caps. Usually min caps are on the higher metal layer. So why did you have to go down to M8 process?
You know, I wish I had done this work myself. I've never been a messenger because I asked that question myself. Why didn't I'm surprised they didn't do that in the first place. I wish I had a better answer for you.